And it looks like Diane is going to introduce Dale, so lucky you. Oh.
All right. One of the wonderful things about this particular club is even though the thing that's brought us together is astronomy and science, we have members who are into theater, into the arts, into the finer points of law and ancient languages, into arcane literature, into musicals, and in the case of a man like our tonight's speaker, somebody who is doing his own precision measurements of Jupiter's moon Io to calculate the speed of light as it was done in the 17th century, but who also is interested in religion, archaeology, is teaching here now at Macomb Community College, and is, well, I hate to use the term Renaissance man, but we have quite a few that you might call that in this club, and I would say that tonight's speaker is one of them. So, ladies and gents, Dr. Dale Partin with The Distance of the Moon.
Thank you for the kind words. I actually became interested in how to measure the distance to the moon 8 or so years ago. I wanted to know how the ancient Greeks had done it. And so, and how they had measured the size of the Earth and the distance to the Sun. And so I read up on that and replicated all their measurements. And using their techniques, you can get the distance to the Sun, the distance to the Moon, to within several percent, plus or minus. I mean, it's impressive what they did with their geometry. They didn't have decimals or any of that stuff. They didn't have iPhones with calculators on them. I mean, they were inventing some of the mathematics that they needed to do these kind of measurements. It was impressive. Their distance to the Sun was off a lot more, a factor of 20 off, but not bad considering it's the first time it had ever been done, and it's quite difficult. Those kinds of measurements gradually increased in precision using more and more modern telescopes and so forth that came along. And then radar happened, and all of a sudden you could measure the distance to the moon within a few meters precision, just blowing everything else out of the water up till then. And then, in the late 60s, well, 1969, the first landing on the moon, and in the early 70s, the United States had its Apollo program, and 3 of the Apollo missions that landed on the moon left optical reflectors, retro reflectors, on the surface of the moon. And then the Soviets, smarting from not having beat us there, nevertheless put a couple of rovers on the moon, each of which had an optical retro reflector that would reflect light back in the direction it came from. So those were used in the 70s to get measurements that amazingly were precise down to something like a couple of centimeters, plus or minus. Just incredible accuracy. And then, and those measurements, by the way, have to some extent continued with time. But more recently, 6 or 8 years ago, Professor Tom Murphy, an astronomer at University of California, San Diego, got into this with the latest equipment, hoping to improve on the precision of those previous measurements. I hope I don't get Ken in the eye with this thing, or Jonathan. And he made what, by comparison, are, I can only use the term, fantastically precise measurements of the distance to the moon. I mean, you might think, well, how can you do that? You know, the moon is this lumpy thing, you know, I mean, how can you measure the distance, I mean, to a scale far smaller than the lumpiness of what's there? Well, you can, if you do things the right way. So, complicating the story is that the distance to the moon is not a fixed number. This shows a picture that I got from Astronomy Picture of the Day, taken with the same setup of the moon at perigee and apogee, when it's, you know, farthest and closest to us, because the orbit of the moon around the Earth is elliptical significantly, something like 13 or 14% difference in diameter, which implies an equivalent difference in how far away it is. We're talking about 13 or so percent of 250,000 miles. And now you're going to measure that's changing on that scale to a millimeter or so? I mean, get real, you know? I mean, it's understandable why the previous teams that worked on this were doing great to get a couple centimeters accuracy. And that's just one of the issues. The moon is wobbling around, right? And you know, if you had something dead center, that'd be one thing. But these retroreflectors are scattered around, so these wobbles are significantly affecting the data. And of course, we're standing on a rotating body, and we're really moving. I mean, right here, we're going around at like 700 miles an hour at our latitude, something like that. At the equator, it's close to 1,000 miles an hour, right? This is big when you're doing millimeter measurements, right? I mean, are you crazy, you know? And worse than that, wherever you put your telescope, it's moving up and down because the ground under it is going up and down. It's flexing due to tidal forces from the moon. It's not just the oceans that go up and down with the tides. The continents are floating on liquid magma, okay? It's worse. The surface of the moon is flexing due to gravity of the sun and the earth, okay? So it's some interesting physics, right? I mean, you rise to the challenge.
Literally.
So, I mean, you know, there's all of that. So, I heard about this work by Tom Murphy, and I was fascinated by it, and I tracked down some of what he was doing, and from here on, most of what you're going to hear, if not all, is from him. And he gave a lecture, Einstein, the Moon, and the long-lost Soviet Lunar Rover, subtitle, Testing Gravity with Lasers to the Moon. So, here's the setup. You can measure the distance from the Earth to the Moon using a laser. Can you see it? I don't know if you can see
I can
some of
see
this.
it. Yes, the green thing horizontally. Yes.
Right here, coming out of this
Right.
telescope, there's a beam going to the moon. May look like the sun, but it's an overexposed moon. And what you absolutely cannot see is a beam coming back that's 10 or 20 trillion times fainter. You talk about single photons that you're trying to detect. Because the beam coming back is spread out over many kilometers. And it's only like a billionth or something of the light of the total amount of photons that went up, because most of the photons you send up there miss the target. Okay. And this telescope is in New Mexico, a place called Apache Point. Here is a picture of Tom Murphy giving a lecture. And this is an iconic picture, needs no introduction, thinking about an equation very few people understand. It's an equation he came up with that expresses the essence of his general relativity theory. His special relativity theory was complicated enough, and that doesn't include gravity. You get into gravity and it gets a lot more complicated. So I'm not going to do too much with this other than kind of give you some essence of things. It's suffice it to say, in physics, anytime you can measure something significantly more accurately than anybody ever did before, physicists love that because it gives them a chance to check any theories that are out there that can explain what you should measure, and what physicists always hope is that the theory doesn't fit the data. Okay? They don't want the theory to work when you check it more precisely than anyone has before. Because if the theory fails to fit the data, and if the data is good, that means there's something missing from the theory. That's an opportunity to come up with some new physics. Okay? You better be right with your data if you say the data does not agree with the theory. This is a picture, sorry that's a little bit fuzzy, of one of the reflector arrays that was left on the surface by the Apollo astronauts. You can see their footprints. They had a mechanism for pointing it to within 1 degree of the Earth. And what this is it's an array of many dozens of small reflectors, corner cube reflectors, designed to send light back the way it comes. I think everybody here knows if you just put mirrors there and light comes in at an angle, it goes off at a different angle, it doesn't go back the way it came. So you have to do something special to make the light go back the way it came. Now, the Soviets landed 2 rovers intact on the surface. They called them Lunokhod 1 and 2. The position of number 2 rover was known to the Tom Murphy team, but the number 1 rover had been lost. Nobody knew exactly where it was anymore. These Soviet rovers, here's the reflector. The French had provided these reflectors to the Soviets. And the rover number 1, for 40 years, nobody had used it, and they lost track of exactly where it was. They roughly knew the position to within about 5 kilometers.
Excuse me. I can remember, about how big was that reflector?
Something like this.
They can target and hit with a laser. And just have the position in the correct place where it's gonna bounce back so they can read the distance.
We can't hear the question over here.
I'll repeat it. The question is, for something, this size, how could they possibly hit that thing with a laser
And have it bounce back to the right place.
and have it bounce back to the right place?
Miles away from.
Good question.
You want the lights off?
That's not up to me. If Jonathan wants the lights off, he can have it.
I mean, because in my mind, I was thinking that it was maybe like the size of a football field.
Oh, no.
Bigger.
Oh, no,
I mean, if you were 250,000 miles away from an object, and you shooting this beam at this object, I mean,
Okay, let me address the question. The answer is they do and they don't hit the target. That is to say, even though they can aim quite accurately, the beam itself is broadened by the Earth's atmosphere, okay, as it goes up out of the atmosphere. And so, and also by diffraction effects from the telescope. So by the time it gets to the moon, it's kilometers in diameter. It's in one of the slides, how many kilometers, a couple at least. And so only a very tiny fraction of the photons of light hit the reflector. Okay? Tiny. And that's what makes this challenging. And then, each of these little retro reflectors is only about this big. And so even though it's designed to send the light back, it's optically designed to send the light back from whatever way it came, within reasonable limits. The fact that each one of those little retro reflectors is only about so big means that the light suffers from diffraction effects. It doesn't go back, all of it, exactly the way it came from. It's spreading out again. So by the time it hits the Earth, I think it's like 10 kilometers in diameter. And even though the telescope is 3.5 meters, more than this, right, in diameter, it's still only collecting a terrifically small number of photons. So they're counting individual photons of light to come back. So it's a great question, and it's amazing what they did, and you'll see a little more what some of the issues were as we go. They knew about where this thing had landed, and they knew that the rover had traveled over many days, weeks I think, something like 11 kilometers, and it had taken pictures as it went, but the pictures were kind of disjointed. It wasn't like a continuous picture. You get a picture of this, and then you're in another place, and here's a picture. And they didn't have, at the time they got into this, high-resolution pictures of this area of the moon. Okay? So they didn't know where it was exactly. This is the highest resolution picture that they had going in to looking for that rover. This is 5 kilometers across, but the resolution is not very good. And it is in there somewhere. Turns out it's up in here someplace, but you'd never know from this picture. So they spent 2 years, off and on, trying to hit that thing and get a signal back. And they never could until...
I know, I gotta shut it off, I'm sorry. I was trying to ignore it.
It's the long ones, works for me.
Sorry.
Okay, now, gravity pulls on a more massive object harder. We all know that, things weigh more of the mass is, but it's also harder to get it moving. Einstein made the connection that gravity is the force you feel as you move through space-time. Here's the inertial mass resisting gravity pulling something down, and gravitation pulling it down. So you can kind of think of Einstein's picture of gravity as in a two-dimensional universe as weights depressing a flexible sheet into an additional dimension, distorting space or space-time. So, Einstein's theory of gravity is a geometrical theory of gravity. Here's a much younger Einstein as he was roughly at the time that he came up with this theory. And he had some great successes with this theory. It had been known before his time that Mercury was doing something weird in its orbit around the sun. Its orbit, like the Earth's, is slightly elliptical, and astronomers had done extremely precise measurements of the orbit of Mercury. And what they found is that the ellipse didn't always go around the same way. It was precessing, is the term. It would keep moving. The closest approach and farthest approach kept walking around in a different direction with time. And nobody knew why. They could measure the effect, but they didn't know why it was happening. And Einstein, did I put this on this slide or the next one? Einstein's theory was able to not only explain the effect, but accurately predict. I can't, you're going to have to move your chair over, Michael, if you want to see, because I can't see the slides if I'm too far back over there. Einstein was able to accurately predict not only the effect itself, but the size of the effect. So that's just an example of his theory, and you know, it's sort of nice, but does it really matter to anybody? That was a common attitude until things like GPS came along, which would become rapidly useless if it were not for taking account of Einstein's general theory of relativity. The Earth distorts space-time enough around it that the extreme precision of the GPS system would rapidly be lost without taking account of Einstein's theory. So that's just, you know, everybody pretty much uses GPS now, and so it's a way of communicating that a lot of things that didn't seem that important when they were first invented have become real important to us. You know, when Bell Labs invented the transistor, you know, it was a nice little amplifier. Nobody was thinking of computers and cell phones that would depend on this stuff, right?
How does gravity well affect the precession?
That's not a trivial thing to answer.
Good, I feel better. Yeah, I thought it was obvious to you.
So,
Nothing
no,
about
it's
general
not
relativity is
nothing.
obvious.
That's absolutely right. Nothing. Or in quantum mechanics. A famous physicist once said, Feynman said, anybody who thinks he understands quantum theory doesn't therefore understand quantum theory.
Therefore,
Yeah, if he thinks he does, for sure he's got it wrong. You know, bringing this to the present topic, the point is that Einstein's theory of general relativity, his theory of gravity, should therefore be able to correctly predict the exact shape of the moon's orbit. If you can measure that more accurately than anyone did before, that's a way of testing the theory. Is it correct? To some new level of precision. And you know, if you compare the predictions of general relativity theory to Newton's theory, you get more than a 10-meter effect in how the moon's orbit looks. 10 meters is huge when you're measuring to millimeter accuracy. So the checks that he hoped to do should measure the distance to the moon to this kind of precision, which is 1 part in 10 trillion. It should also be able to test whether the sun's gravity is pulling on the Earth or on the Earth and on the Earth's gravitational field. Think about that. What is the mass of the Earth? Well, it's some number. But when you consider the fact that the moon is attracting the Earth and the sun is attracting the Earth, they're attracting not only the Earth itself, but the Earth's gravitational field. Einstein's theories, as special relativity theory, show that there's an equivalence between mass and energy. There's energy in the field, so that there's an equivalent mass associated with it that you can calculate. And that gets included in these gravitational effects. And this thing with the Earth's gravitational field amounted to a 13-meter shift if the Earth's gravitational field was not being attracted, okay? And by the way, this is generally true. Electric fields and magnetic fields, nuclear force fields, all have an equivalent mass associated with them. There are a lot of complications. What is really needed is to measure the distance from the center of the Earth to the center of the Moon. Because everything else is, getting squished all around by gravitational effects and so forth. Even barometric pressure effects will push down the crust of the Earth slightly. Slightly matters here. So that's what ultimately has to be measured, even though the measuring equipment is confined to the surface of the Earth and of the Moon, and the surface is not stationary or rigid. Everything is on the move. The Earth rotates, depending on what your latitude is, at hundreds of meters per second, and you're measuring to 1,000th of a meter, right, a millimeter. The Moon is going fast. Both of these are orbiting the Sun fast, and the Earth's surface is floppy. Tides move the surface as much as 2 feet, even remote from the ocean. At this Apache Point place in New Mexico, tides on the California coast are flopping that whole part of the crust up and down, okay, by 2 feet. High and low pressure atmospheric systems, weather systems, change the pressure on the crust and can push it down or let it come up a little. Even groundwater flows can be detected, flowing in the ground down underneath. So how? I mean, you can measure atmospheric pressure, right? And figure out a correction factor for that. I'll get to how you deal with flexing of the Earth's surface in a moment. Here's a picture of Buzz Aldrin with one of the retro reflectors, placing it on the Moon. Yes, we really did go to the Moon. Apollo 11 and 14 reflectors have about 100 corner cubes. Apollo 15 had one with 300 corner cubes. This is what these cubes look like in a little more detail. And here they are, here are their positions on the Moon. The 3 Apollo ones are deliberately in a triangular pattern. Okay, so that was helpful in measuring how the Moon is wobbling back and forth, right? Then the 2 Soviet probes are here and here. And this is the one that could not be found for 40 years, but it was highly desirable to find it because it's so far out toward the limb of the Moon. It makes it possible to more accurately measure the Moon tilting back and forth, if you can find that one. Did I cover what I need to cover here? I think so. So this is not your father's Apollo. I think he's talking about people like me. Okay? This is they call this an Apollo program to measure these things, but Apollo stands for Apache Point where the telescope is, Observatory, Lunar Laser Ranging Operation, okay? And they were hoping to improve the state of the art by a factor of 10, from something like 2 centimeters to 2 millimeters, 1 if they could get it. So any good manager knows that the first thing you have to do is come up with a clever name for something. So that's what they did here. And they started over from the ground up. Didn't just try to adapt old equipment. Everything was state of the art. So I think people here, most people here, at least the older ones, would remember when we had astronauts on the moon and people in mission control would talk to them. You could hear this 2.5 second delay between when mission control would ask a question and you'd hear the answer come back. So it takes 1.25 seconds at the speed of light for the radio waves carrying the question to get to the moon, and 2.5 seconds to get back, plus a normal pause while somebody thinks how to answer. So that's, radio waves, light waves travel at identically the same speed in vacuum. It's all the same stuff. It's photons of electromagnetic radiation. So they're firing 20 pulses per second. That means in 2.5 seconds, there are 50 pulses in play at all times, right? And they're keeping track when a pulse comes back, which one was it. Each pulse is 1/10 of 1/1000000000th of a second in duration. That's 100 picoseconds. At the speed of light, light travels 1 foot per nanosecond, approximately. So that means in 1/10 of a second, which is how long the pulses were, roughly speaking, they're about 1 inch long, traveling at the speed of light, right? About this long. Because they need that kind of resolution. They actually need far better resolution, because that's 2 or 3 centimeters, and they want resolution to 1 millimeter. So even that is big, okay? But by doing averaging, they can pull out, if they can collect enough data points, they can get it down to close to 1 millimeter accuracy. That's incredible. But what you get into is, if you see, here's the problem. One of the ways you block out moonlight is by putting the appropriate green filter over your optical detector to screen out other colors of light, okay? However, the more you compress that light pulse, you start spreading out the wavelength to where it's no longer a laser like ultra narrow frequency or wavelength of light. It becomes broader. So there's a trade-off there. You can't make that pulse too short. So, even though this is a laser being fired out of a 3.5 meter telescope, atmospheric, so it's highly collimated, but atmospheric effects broaden the outgoing pulses to about 1 arc second. So by the time you get to the moon, that's a 2 kilometer diameter, addressing your concern. 2 kilometers, and you're trying to hit this little target. That means less than 1 out of 100 million photons of light hit the reflector. Now, the reflectivity of the moon unfortunately, is really crummy, right? Because you don't want to get too many photons coming back that miss the reflector, but hit the moon and still come back to you. The reflectivity is something, the albedo, something like
7%.
No, actually, I've been seeing 13% on sources I've looked at.
All right, well, that's, 7's an average,
It's low,
yeah,
okay?
an average.
Plus, even more important than that, because that would, if all of those came back, it would overwhelm the detector. They mostly go in other directions. Almost none of them happen to go back exactly in the direction the pulse came from, right? Almost none. Good thing. If you're hitting a rough surface, you know, re-emits in the whole hemisphere. Jonathan, keep me on track for time. Will you give me 20 minutes? Could you give me like a 10-minute warning? Sure. Can remember. Okay, so the pulse gets to the moon. It's 2 kilometers in diameter. A tiny less than 1 in 100 million photons hits the reflector. Those that do get reflected back, but those little reflectors are only about this big, and diffraction effects therefore greatly broaden the beam. This is a much smaller thing than the telescope that launched this beam. So by the time the beam gets back to the Earth, it's even bigger, 10 to 15 kilometers in diameter. Less than 1 in a billion of the return photons enter the telescope. Fortunately, the telescope is at least bigger, right? It's 3.5 meters in diameter. This is a picture of it. This is the telescope being used, 3.5 meter. This is the laser at the Earth end. This is a close-up. The laser is mounted on the telescope. The primary mirror is down here. Here's a secondary mirror. This shows it when the laser is operating. You get enough scattered light that's not going straight out the tube that you can see it. The loss in photons is staggering. 1 photon in 10 to the 18, right there, completes the journey and makes it back to the telescope. Just to try to give you a sense of that number, if each photon is represented by a grain of sand, roughly a millimeter on the side, they launch a cubic kilometer of sand to get 1 grain of sand back. That's a little over half a mile by half a mile by half a mile of sand. You get 1 grain back. So, if they're going to have a 1 arcsecond beam width when they get to the moon, they require 1 arcsecond pointing accuracy. That's really good accuracy. That's equivalent to looking at a quarter from 3 miles away. And everything is moving, right? Flexing, we're rotating, the moon is moving. It's not like you're aiming at a steady target. The moon is typically moving across the sky at 15 arcseconds per second. So you have a computer adjusting precisely where you're pointing for every pulse. Plus the distance is changing up to 400 meters per second. That's 400,000 millimeters per second. And so you have to be taking that into account. You cannot blind the detector. The detector will see, even with the green filter in front of it, it'll detect, a lot will get through of just moonlight, not from your laser, just sunlight bouncing off the moon, really bright. And you're going to get a lot of it. And you're trying to detect single photons. So you turn this detector on and off really fast, so that when it's off, it doesn't register photons and get swamped. And they have to know exactly, and they're turning on for 100 nanoseconds, and they have to know exactly when to time it. When the pulse that they shot 50 pulses ago should be coming back, right? Because there are about 50 pulses in flight at any time. So they only open their eyes at the detector, so to speak, when they expect the light to come back. Another issue is the reflectors are fixed on the moon. So as the moon wobbles around, the reflector, you know, if at one point it's dead on perpendicular to the laser beam, later on it'll be at an angle. And so some of the laser beam hits a retroreflector at one distance, and another part of the laser beam hits the reflector where it's closer, so that spreads out the return signal in time. And they can see that. This is time, and you know, the window in which they get pulses starts to get fatter in time as the moon tilts the reflectors away, and narrower as it tilts them back to be more nearly perpendicular. Typical nightly measurement precision is 1.5 millimeters. Sometimes it's close to 1 millimeter. So they can determine exactly how misoriented the Apollo astronauts left these things. Okay? So how do they deal with the Earth flexing around? They do it by measuring the distance to the center of the Earth to within 1 millimeter. Okay? What they measure is not the actual distance, they measure changes in that distance. That's what counts. And the way they do that with an instrument, it's in this chamber that keeps it in liquid helium at 4 degrees Kelvin. Inside there is a levitating superconducting sphere such that it's sensitive to changes in the Earth's gravitational field on the order of a millimeter, actually less. So whatever it is that the Earth is going up and down, it sees that as less gravity, because it's farther from the sun of the Earth, or more gravity. Right? So they can detect a millimeter, actually less, of the change in the distance to the center of the Earth. Here's what the data from that thing looks like over a month. Here's the shift in G, the acceleration due to gravity. There's a couple of different effects mixed in here due to lunar tides and solar tides. Solar is the daily thing, right? Actually, no, the solar is the subtle stuff. And buried in here is also effects like atmospheric pressure changes. But those are smaller and harder to see on the scale. So, here's how big a signal they theoretically should get, called 100%, from the reflectors. Here's what they actually get. A big dip near full moon, down to 1% of what they would theoretically expect. Most of the time, they're getting a whopping 10% of what theory would predict. So the question is, why? What's going on here? Most likely, it's dust that has accumulated on the optics. That was not anticipated because there's no wind on the moon like there is on Mars, right? Coating solar cells and cutting down on efficiency and stuff like that. There isn't any wind on the moon, except there is. It's called the solar wind. What it does is you get charged particles from the sun hitting tiny dust particles on the surface of the moon. And these solar particles, mostly protons, have an electric charge. And when they hit a dust particle, they give it a little charge. And maybe a few more protons hit it, give it some more charge. And the surface around it is also getting positively charged, so it repels and lifts a dust particle up slowly off the surface of the moon, and it may wind up landing on the retroreflector. And it's been 40-some years, right? It doesn't take much.
Has there been any noticeable dip in the reflectivity?
Well, I showed the data, it's 10% of what they
Right, but I mean over time, is it getting worse?
I didn't see where they
been
said
doing
that.
it that long.
Huh?
They haven't been doing these.
Yeah, I don't think they know yet.
They'll come back in 30 years, try again.
So, what they've realized, you know, the light beam has to go through the top surface twice. And so they can kind of estimate how much dust, what percent dust is on the optics to give a 10% effect. And then there's something else that goes on when the full moon is coming straight into, when the sunlight is going straight into this thing. It heats it up more. The heat of the sun will warm this up, and the optics bulges slightly. We're talking way less than one wavelength of light. But what it does is it spreads the return pulse out, and they lose another factor of 10. So the reflectivity goes from 10% down to 1% when you're close to a full moon. It only warms it up by about 5 degrees centigrade. That's all it takes. So dust on reflectors is believed to be the culprit. I think I basically covered this. Now,
10 minutes.
okay, finding Lunokhod 1. You might think, well, let's just keep blasting away, aiming at different places, right?
Right.
Right? I mean, where's the problem? Well,
Took a year.
you know, it took 2 years and they didn't find it.
Ooh.
They have since found it. On and off, whenever they had some spare time, they keep the laser on trying to find it. But it's not just knowing what spot to aim for. It's the fact that you're only opening the eyes on the detector for this tiny little piece of time. And they have to know when to open the eye, to turn on the detector. So the effective search zone, I think I showed in the next slide, is where is it here? It's 2 kilometers long, but it's only 20 meters wide on the surface. Let me see, yeah. You know, because the surface is curving away from you. And so if there's something just beyond, just a little farther away, the light takes a tiny amount longer to get back, and you've already closed the detector down to stop it from being swamped with photons. So the effective search zone is 2 kilometers by 20 meters. So they tried to collect all the data they could for where this lunar rover had gone on the surface and identify what these craters were that had taken pictures of. But no high-resolution imagery existed to identify the crater field. One group that tried to look at the data and figure out where the thing was turned out to tell them to aim 4.5 kilometers in the right spot. Then came the Lunar Reconnaissance Orbiter to save the day, launched in June 2009. High-resolution camera, laser altimeter, lots of good stuff on it, and they identified it with reasonable certainty that they were seeing it. And they opened their window up from 100 nanoseconds to 800 nanoseconds to stand a better chance. Here's a picture of the correct area, and this little blip here, when you blow it up, you know, there it is. Found both the lander and the rover. Even at this, it doesn't jump right off the page at you, right? And it turns out, you know, it's right in there somewhere on their original photo. Here's where they tried aiming in that spot, and they almost missed it. Right at the edge of their data, they were seeing something. So they readjusted their window until, and here it is. They had their window open a lot wider, so they're getting a lot more noise. They found it. And they've done more precise measurements. I'm going to skip that. So it's really good that they found it because, as I mentioned, it's out closer to the limb of the moon, so it's more, it lets them measure more accurately the libration of the moon wobbling around. I'm going to keep going. So, basic science research, this is his pitch at the end of his presentation for continuing to support him doing this. Basic science research is where today's explorers go. There will always be a frontier. We aren't smart enough to foresee the impact of our ventures. General relativity theory seemed academic before GPS came along. Lasers were thought to be a cute laboratory demonstration of quantum mechanics until they started cutting steel with them, right? Doing all kind of other stuff. Inventors of the transistor were thinking of them as a transimpedance amplifier, not computers or iPhones. So he's saying you never know what the payoffs may be for basic research. That's what he's saying.
Yeah.
So he says, let's hope we're smart enough. This is being directed to funding agencies. Let's hope we're smart enough to continue such ventures. I, Tom Murphy, for one, am very lucky to do something so fun and rewarding. And that's the end.
All right.
Questions,
I
comments?
do. Obviously, when you put these reflectors on the moon, that's before the laser technology that made it possible, so that was intended for radar targeting, or?
Lasers did exist
But
and were used in the years immediately afterwards to do these measurements. It took a couple years to get them working right, but they were getting accuracy to within a couple centimeters.
okay,
Okay.
so they were successful, as you described, for the ones that had essentially targeted on the moon. The one that was more peripheral, the lunar one, that would be
Right.
more difficult to
Right.
target because
They didn't know where it was exactly.
you know where it was. Plus, I would think the angular position of the moon would create
That's right.
a broader spread of the laser when you hit the moon in that
That's
area.
true. Actually not, because the reflectors tilt to point at the Earth. However, if you're off a little bit, you're at a way larger distance away from the correct distance, so it's harder to find it. Is there? Yes.
A couple of questions. One is, so by the method you've outlined, you can determine very precisely the distance from the source of the laser to the mirror back to the detector. And then you've got the gravimeter, I think that's the correct pronunciation, on Earth that can determine the position from a specific height to the center of the Earth with a millimeter accuracy. How do you get that degree of accuracy from the surface of the mirror on the moon to the center of the moon? That's the gravimeter on the moon somewhere.
Well, by getting an array of 5 sensors, you can see, in effect, you can measure how much the surface of the moon is bulging out
Okay.
or not, right? You can measure all 5 of them. And they'll do one for a few minutes, and then they'll move over and do another, and then move over and do another, and then go back and do them again. So you can figure out from your data what the bulge
The
is.
deflection for all those points, but at the same time though, the moon is not a perfect sphere, it's a way spheroid, and that it complicates things a bit.
Yeah, it does. I didn't say it wasn't complicated.
Okay. There are probably models for that can probably take those 5 points, look at the deflection over time. Because, I mean, it's not that it's.
That's why it was important to find that additional rover. It really helps when you've got a
I mean, if the moon's a perfect sphere, I think it's pretty easy to figure out how you can calculate that, but it's this lumpy, not spherical mass, and that just, to that kind of resolution,
Yeah.
without any kind of gravimeter, it seems to be, it would be difficult. And one other
Go ahead.
thing I want to throw on is, the dust explanation for the loss of performance on the mirrors. I think a better explanation might be sputtering from the solar wind, increasing the surface roughness on the optics. Have they considered that?
I didn't hear any consideration of that. The sputtering effects would have to roughen the surface quite a lot, right?
Precision optics, right? And you're
Yes,
talking-
but, you know, it
years.
had to be, you know, something like 10 wavelength or so before you start to see any change in reflectivity, I would think.
Well, I mean, it's roughness, but it's also, I don't know what that first optical surface is. Is it a mirror surface? Is there some?
No, it's not a
Okay,
mirror.
it's just it's a prism, right?
It's
So
probably quartz.
okay. So how
It
much?
can't be a mirror, or it wouldn't send light back the right way.
Well, yeah, that's a good point. So it's essentially a quartz prism.
Yeah.
I wonder how much surface roughening you get from sputtering over, say, 50 years of time.
We will go and find out.
I better take more questions.
I think two more.
It's just the change in the distance. I think you had an incredible number there. Do you recall the change in distance over time to the moon, the actual change?
Yes, the moon is moving away from the Earth at, I think, 3.8 centimeters per year. Due to tidal effects on the Earth, it's making the Earth slow down.
Change in distance.
Because it's transferring angular momentum from the Earth to the moon, from the Earth's rotational motion to the moon's orbital motion. The theory is that when the moon was created shortly after the solar system started by a big impact, the moon existed as a ring of debris around the Earth that wasn't very high up. I forget the number, maybe 10,000 miles up.
So,
And it coalesced into the moon, and it's going on at orbital velocity, and the moon and the Earth was really rotating rapidly, 6-8 hours per day, and so over time, the moon, which coalesced out of that ring, has this has been going on slower and slower the farther it gets towards 3.8 centimeters a year now.
I think I meant the change due to the angular and the orbit.
Well, the
It's
change.
been the same.
Miles an hour was changing.
Okay.
The
Yes,
actual
Jeff.
distance.
The 1 cubic kilometer of sand, was that per pulse?
Yes.
Okay. And then my second question is, I work with reflectors and laser rangers every day, and I've always wondered, you mentioned, when it's on a little bit of an angle, one will hit closer. And I've always thought about it like, if it hits on the outside, its path through the 3 mirrors will be longer than if it hits further down in.
What they're comparing is you've got an array of these things.
Yeah.
And so as the array tilts, this retroreflector closer to the Earth gets the pulse before this one does. Not a single retroreflector tilting, that's
But
not.
but when you're measuring to the millimeter,
Sure, if the tilt's big enough, the tilt isn't.
well, but not even the tilt, you've got the reflector. If the beam comes in and hits this side and it bounces around and comes back, it'll be one length. But if it comes in closer to the center, where the mirrors are closer, it'll have a different length. Is it just average?
Same length.
Well, mine are 3 inches.
I
can explain that.
Yes.
Imagine a wave, a plane wave coming in, and if you trace the wave, it gets scrambled as it goes through, but it comes out as a plane wave coming out. So the distance is the same regardless of what part of the reflector it hits.
Really?
Actually, it's a good way of explaining it, yeah.
Okay.
So, any final questions, because we're 2 minutes over? All right. Thank you. So after our Macomb meetings, a number of us go to the Applebee's restaurant on 12th Mile at Van Dutch. And so if we would like to continue the conversation, please have them there. We have one volunteer for a grill, so I think we should be set on the grill front. Could always use a second. But we have no volunteers yet for coolers and ice, so if anybody can bring one. All right, we have 1, 2.
I'll bring a cooler and 2 bags of ice.
All right.
All right, but isn't there a
All right,
nice place
3. That sounds
east on
good.
the Mile Road?
Yeah.
All right,
Yeah, that's true. We could always go.
There's a country store there.
Alrighty, sounds good. See you on
next
Saturday.
Saturday.
That was just to circulate around. We could add him to the archives.
Excuse me?
Good night.